So today we are very happy to host the webinar Enhancing Air Quality Sensor Network for Citizen Science. Citizen science involves public participation and collaboration in scientific research to increase scientific knowledge. Despite its potential, producing citizen science collected data that is perceived as trustworthy enough to be published in peer-reviewed scientific articles and influence policymaking remain a challenge. In part due to the issue involving data accuracy and standardization. So today we will have 3 short talks by 3 experts belonging to 3 EU Horizon projects, as I said, COMPAIR, FUNsnm and SOCIO-BEE. The idea is to discuss, exchange experience and lesson learned to improve the reliability, to improve the air quality sensor networks. The session will be also conclude with a short discussion, panel discussion between the speakers, but also with the audience. So we'll start with a talk by Bram Verbeek. Bram Verbeek is a researcher working on air quality measurement at the Flemish Environmental Agency, which is part of the EU Horizon Air Monitoring Citizen Science Project, COMPAIR. He has a background in theoretical physics and holds a PhD from the University Catholique de Louvain. He is particularly interested in the use of low-cost sensors for air quality monitoring and in the development of advanced data analysis techniques for such measurement. Today, he will talk about local source detection using mobile low-cost particle matter sensors. So Bram, I invite you to share your screen.
Let's see. You see my screen now?
Yes.
All right. Yeah, thanks for the introduction. So I'm going to talk about local source detection using mobile low-cost particulate matter sensors. This is a project that we did in the context of COMPAIR, so citizen science-oriented project. But it was more of a little bit of a pilot study, and it's something that we plan to continue on in the future. So really, this is just a small experiment, let's say, for this type of workflow. So these are the contents. I'll start by introducing the topic a little bit. I don't know if everyone present here is an expert on air quality or not, but I will give some basic introduction on it. I'll talk about PM sensor measurements, difficulties involved. I'll talk about a bit of the data processing. I'll show some results that we got from our trial, and then at the end, I'll give some conclusions as one is wont to do. All right. So let's start with the question: what is particulate matter? So particulate matter, essentially, these are particles that are suspended in the air, and that we basically take into our bodies by inhaling. So the typical measurement that people use, or the typical scale that people look at, is particles with a diameter in micrometers. And in particular, there are different types of classifications that we put on PM, depending on how deep they penetrate into our bodies when we inhale them. So coarse particles, PM10, that's a diameter of less than 10 micrometers. They typically stay in the upper respiratory tract, or they are able to penetrate the upper respiratory tract. Then the portion of that is able to penetrate into the lower respiratory tract, we call fine particles. This is PM2.5. And then you have even finer particles, PM1 and PM0.1, which are basically nanoparticles that can penetrate essentially into our bloodstreams and the whole body. Of course, the smaller the particles get, the harder they are to measure. So the sweet spot, let's say, for these types of measurements, and especially these sensors, is PM2.5. So that's what we'll focus on today in this talk. So we'll look at the PM2.5 fraction, which is a little bit the Goldilocks zone between health impact and also measurability. So where does PM come from in principle? Okay, so one source is traffic, not only combustion engines, but also brakes, tires that roll onto surfaces, so they create dust, and these fine dust particles can be inhaled. So traffic in general is a source. Construction works is a typical source that can cause like local spikes. This of course creates a lot of dust, creates a lot of pollution in the air. Then there are any kind of organic matter that burns. So this could be a natural occurrence like a forest fire, but it could also be fossil fuels burning. It could be intentional wood burning, anything like this. And then industry. And of course, there are many more sources, but these are like the typical things that people think of when they think of man-made sources, let's say, the man-made primary sources, I should say, of particulate matter. So that's where it comes from in principle, or where it could come from, but where does it actually come from in practice? If we look at the data from Flanders, so the emission data, here we see a little bit of a pie graph showing these different percentages. This is based on just emission statistics in Flanders, and we see that the dominant primary source of particulate matter in Flanders, this is data from 2022, but this won't have changed much by now, was domestic in character, which means that it's related to residential areas, people living. And in particular, the driving force in this context is domestic heating via wood burning. This is by far the primary source within Flanders, emissions-wise. So if this is the primary source, and we go to the VMM website, where you can find this nice model map of Flanders, you take a screenshot of some random point, you see, okay, this is the distribution of PM, so you can estimate at each point more or less the concentration. But if I just said that the major emissions are domestic, well, I don't see many domestic sources on here. I see some major background, I see the main traffic lines, let's say, but I don't see any domestic sources. And the reason for this is that essentially this map is made using the data from the monitoring stations, which are these little dots on the map, and then interpolating this using a model, and also involving traffic information, traffic flow, to essentially take on this information as well. But this model does not have any info on these local sources. So essentially, we have no idea where they are. We have to go look for, we have no idea what is the distribution of these local sources. We have no idea what's their intensity, what's the time frame at which we can expect them to emit, what is the distribution of their emissions, because of course you can test domestic wood burning in ideal conditions, but there are very different ways of doing domestic wood burning. So these are all questions that we have, and we as of yet don't have a very good monitoring system for it. So as I said, the lack of precise knowledge of these local sources is because the monitoring network essentially is too widely dispersed. This map has all of the monitoring stations that measure particulate matter in Flanders. And even though there are quite a lot, this is still way too wide to go and check for local sources in some residential area. I mean, there are large parts of Flanders that essentially have no monitoring station even nearby, so you can't even estimate the background. So this is where citizen science comes into play. Essentially, what if we use citizen science? We use sensor measurements, mobile sensor measurements, to try and learn more about the locations of these local sources. So what's the basic principle of these sensor measurements? These sensors are small, compact, usually quite cheap devices that that measure air pollution, but they don't measure it as precisely as, say, some European approved reference monitor device. So they're based on some physical principle, but they have a much bigger error margin. And the physical principle that these PM sensors are based on is the optical measurement technique. So essentially, the basic physical principle is why can we see smoke from a wood fire? If we start a campfire, we can typically see a lot of smoke. And a lot of this smoke you see here will be, of course, water, but there are also actual pollution particles in there. Why do we see it? Well, it's because it scatters light. These particles, when light hits the particle, the light gets scattered. And because the particles are typically larger than the wavelength of visible light, which is in the hundreds of nanometers, they get scattered uniformly, essentially. There's no distribution between the wavelengths. So in this right graph, you can see that essentially this scattering also depends on the particle size. The bigger the particle is, the different angular distribution will be of the scattering of the light. And that's important because that's the basic physical principle that these sensors use. So the idea is, well, you take some airflow, take it in some stream of air, and then you put a laser beam perpendicular to this stream, put some light absorber at the end, and then you put a sensor in the middle. And essentially, this sensor is going to see what is the scattered intensity of the light beam, of the laser beam. And of course, the bigger the particle, as we saw before, the more forward scattering there will be, the less sideways scattering. So here also you can see a graph. Depending on the angle that the laser has compared to the airflow, you get a different response particle size-wise. And this is what these sensors use to estimate particle size, and then it counts the number of events, let's say, the number of scatterings. And this it uses to estimate a concentration, and then altogether you can get an estimate of the total mass of air pollutants per volume in the air. So a concentration. That's the basic idea. In principle, the sensor that we used in this experiment was the Sensirion SPS30. So that works exactly as I described before. Ambient air gets sucked in by some blower fan. You have a laser hitting it, and then a sensor and an absorber. So that's basically all it is. But we didn't just use this Sensirion SPS30. We used the SODAC sensor, which is basically an extension that has this Sensirion built in. And the SODAC sensor, the particular thing about it is that it has a GPS module built in. So essentially, you can give this device, has a built-in battery, everything, to a citizen and tell them, go walk around and measure as much as you want. And in the end, you will get GPS data, temperature, relative humidity, and also concentration data. So what does this data look like that you get? Well, you get concentration for PM10, PM1, and PM2.5. We're interested in PM2.5. We get GPS coordinates, latitude and longitudes. We get a time coordinate. We get temperature, relative humidity. We get an EMA, which is some identifying number per unit. Of course, this, without any context, without any input, is not so interesting to look at. It's just a big table of numbers. And you could start thinking about, okay, what's the concentration at this time? But the problem is that all of these measurements basically have to be taken within context of the trajectory that they were a part of. So that's the first thing that we're going to do. We're going to split up this data set into trajectories. We're going to study the data per device. And at any interval that is larger than 5 minutes in between measurements, we're going to truncate the trajectory. So we're going to assume that whenever a citizen was not moving for more than 5 minutes, that basically means the end of that trajectory. What's more, we demand that any trajectory be made up of at least 30 measurements. So it needs to be at least 5 minutes long. The reason for this is that the SODAC sensor doesn't have an on or off switch. It basically starts measuring as soon as it detects GPS movement. So sometimes you could get problematic measurements if someone walks around with the sensor in their house to plug it into the charger or whatever. So we want to filter out a lot of these bogus data as much as possible. Okay, now the problem with this this whole game is that, well, for one, these sensors are not so accurate, so they depend on a lot of meteorological constraints. But beyond that, there's always a very significant effect from the background for a particular matter. I mean, there are days where the background is much higher, much lower. So it's very hard to really take into account the concentration at face value. You have to compare it to some kind of background level. And what we decided to do for this experiment is basically look at a net contribution. We're trying to detect local sources, so this makes a lot of sense. We're trying to find where is the concentration much higher than 2 streets further, essentially. And the idea of this net variable is to take the 10% quantile PM 2.5 throughout the trajectory. So we take the dividing up all the data, we take the 10% lowest, and we subtract that from all of the concentrations. And if this difference is more than 10 micrograms per cubic meter, then we consider the data point an event. We consider this like a extraordinary spike in the data. So here you see an example of an event. You see that the background concentration, or the 10% quantile, let's say, would be around 4 micrograms per cubic meter, and these spikes are around 14. So this is exactly 10 micrograms per meter higher. This is some threshold that we decided by looking at the data and deciding that this was probably a good threshold. So this is not based on any deep scientific knowledge. This is just a decent threshold to use for now. But we have a problem if we do this type of analysis, which is that the trajectories are partly made up of indoor measurements. If we give a sensor, a mobile sensor, to a citizen, we say, go walk around and measure the concentration in your neighborhood, then it might happen that they strap the sensor to their backpack, they go for a little stroll, they pop into the bakery to buy some bread, and then you have some indoor measurements. And this will really mess up your analysis because we want to subtract the background. But if the background is indoor, it's going to be significantly lower. And so this is going to cause a lot of problems. So we have to get rid of these indoor measurements. Luckily, since we are doing this experiment to track down wood burning, in particular, we do these experiments in winter. And so that means that we can essentially ignore any data where the temperature is more than 15 degrees, because outdoor temperatures in Belgium during winter are pretty much never 15 degrees or more. So that data definitely is indoor data. But that's not sufficient because the temperature sensor has a little bit of a lag compared to the GPS and the concentration sensor. So we're also going to ignore any data where the distance between sequential measurements, which is every 10 seconds, is less than, sorry, that's a typo, 5 meters. Or, well, we demand that the distance is more than 5 meters, then it's not a typo. So anytime someone's basically stationary, someone's basically not moving, we will ignore this data. And this is a quite crude filter, but it works quite well to clean up the data set as much as possible. Okay, now all of this talk about cleaning up data and how the sensors work. Let's get to the actual experiment. So we did this experiment in Hove. Hove is a small town outside of Antwerp. It has about 8,000 inhabitants, and it's about 6 square kilometers. We worked with the Environmental Council of Hove as citizen science during the winter months, January to March of 2024. This meant we have 8 people, including one of our colleagues, which is how we actually came across this experiment, is that one of our colleagues is also a member of the Environmental Council of Hove. So he was essentially the, let's say, the local connection to this experiment. We also asked participants to keep a diary, because that way we could validate the data that we got afterwards and also contextualize it a bit better. So what do these trajectories look like? I'm going to try and play the video. I hope it plays well for everyone. So this is, if we built a little data frame viewer to check these trajectories ourselves. This is essentially what they look like. So now you can see the citizen walking around with the sensor. And we basically told them, like, do whatever you want. We left them as free as possible, but you could tell quite early on that people caught on to the idea and started purposefully walking around and looking for places that essentially had spikes for wood burning. So there was a little bit of a Pokemon Go effect, let's say, where people, if people go out to measure things, of course they want to measure something. So you could see a lot of trajectories like this where people measure quite a lot of spikes. And the interesting thing, of course, about comparing this data like this is that you see quite a lot of spikes, but you can also see now, looking at spatial temporal data, that essentially they're passing by the same let's say, zone or hotspot multiple times. So a lot of these spikes are actually identical sources. Yeah. So we use this kind of data frame visualizer to essentially validate the data, see if there's any kind of bogus trajectories that we had to get rid of. After all this processing, we had 7 active devices, traversing a total of 77 trajectories from January until March 2024. The total distance traveled was 480 kilometers, so that's quite a lot of walking and cycling for our citizen scientists. The average trajectory is about 6 kilometers long, and essentially the trajectories could be split up into 2 types. The daily trips, which is people's commute, people going to the shops, people walking the dog. You could really tell there were one-way trajectories because then they got stationary and the trajectories were truncated by the algorithm. And they were essentially daily or very regular. These types of daily trips typically were less useful than the second, which are the focus trajectories, and that's people really going out to hunt for PM sources. But you can see that in this case, both of them essentially measure the spike. So if you're lucky that someone's commute passed by a hotspot, then we still manage to get that data. Okay, then what happens if we really put this data on top of the map of Hove? So this is the number of passes in 100 by 100 meter grid cells. You can see that people mostly pass through this area here. I don't know if you can see my cursor, actually. Can you?
Yes, it's small, but we can see it.
Okay, good. Yeah. So in this central area here were the most passes, obviously. So that's places that got the most traffic, and then sort of the outskirts of the town, there were quite a bit fewer passes. You could see people maybe doing like one-off trajectories or just a couple passes. What happens if we look at the number of events? Well, then we can see clear hotspots. So if we just look at the distribution of the events, we can really see that we go from a very spread out map that goes all over Hove to very clear identified locations where problematic things were measured. And we see 2 big hotspots in particular. So these would be interesting zones to measure further. But of course, these 2 hotspots are also in the area that got a lot of passes. So we need to be a little more careful. We can introduce a relative number of events, which is basically the number of events divided by the number of passes for each grid on the map. And then you see that these are a little bit suppressed. You can see 2 further away points that are a bit elevated. But then we introduce another problem, of course, because there are more passes that are outside of typical, let's say, wood burning hours. So we can restrict this data to the main wood burning hours, which is from 4 until midnight, let's say, when people get home from work and they want to heat their homes. And then we still see those 2 major hotspots in the center, so one along this main road and one in this area here. And we see 2 potential spots on the outskirts, but they had low amounts of passage, so they essentially need more investigation. If we look at participant diaries, they essentially confirm that the vast majority of these sources, so over 95%, were of wood smoke. There were a few one-off events. Someone passed by with a cigarette that accidentally got picked up. Someone walked by a cemetery and picked up some incense being burned. But the vast majority of sources were wood smoke. So that essentially confirms our suspicion that in a residential area like this should be the dominant factor. Okay, so what did we learn from this small trial? I mean, we managed to get a little bit of data out. We managed to get this map of the hotspots. What did we really learn, and what do we want to do in the future? Well, first of all, what we learned and maybe what we should do better in the future. We learned that these mobile sensor measurements can be a useful tool to try and track down these hotspots of local source residential context. Also saw is that this type of setup is very demanding for participants. We require a high time investment. We ask people to go outside in winter when it's cold and raining, and Belgian winter is not that great, so it's not a very fun time to be outdoors in the evening. And we also want them ideally to keep a diary, and so it requires really a lot of investment from our citizen scientists. So potential answer to this would be to target specific groups, maybe run clubs or people who own a dog and need to walk the dog every evening anyway. We need to think about this a bit more to really try and lower the time investment for people as much as possible. Something that could certainly use refinement is the data processing pipeline. It's quite crude now. A lot of the thresholds that we put in basically, just by trial and error. And so we could really try and think a bit more about what could be good physical or principles to really, give these thresholds a little bit of a foundation. Another question, which is maybe a bit broader within the context of this experiment, making this type of data public, of course, raises questions with respect to privacy. First of all, people's trajectories obviously shouldn't be made public like this, but also maybe a hotspot map could, raise some accusatory sentiments towards people who live in these hot zones. So, I mean, this is a complicated issue that needs to be thought about a bit. And another thing that we learned was that any device used in these types of experiments must be as simple as possible. Really, the idea that you have to kind of learn and get to know this device to measure with it very efficiently was a little bit of a challenge and made our data cleaning a little bit more complicated than maybe it should have been. We noticed that the data coming from our colleague, who of course knows this device quite well, was significantly cleaner than the data coming from citizen scientists, which makes a lot of sense. But I think these are things that can be solved by doing small technical interventions on the device. So what are possible next steps? What can we do with this data? Because now we have this map of this small town. We put a lot of effort into, or at least these 8 participants in particular put a lot of effort into creating this map. But what is it really good for? I mean, this doesn't really give you any continuous data. It doesn't improve the knowledge of your monitoring network. It just shows you, okay, maybe these would be good places to keep an eye on. Well, that's exactly what maybe would be the next logical step. We could install stationary sensor measurements in the determined hotspots in Hove, and we could see, well, if these stationary measurements manage to capture the effects of local wood burning, the mobile measurements are essentially a first step in this process. So we could, if a town has a problem with wood burning or there's a big local issue around this, we could use mobile measurements to inform where would be good places to install some sort of stationary sensor network. And then we could, really get continuous monitoring, and we could really get integrated whole data over the entire winter period. That would give us more information, both about what are the emissions like in a small town like this, which would then feed back into our emissions data, but also from a bigger point of view, really tracking down these local sources and understanding their distribution a bit better. And then a second thing, of course, would be to repeat this type of experiment in different locations. So Hove was just very convenient. There was an environmental council. They wanted to do something. This colleague of ours was part of this environmental council, so it was a very clear way in. But maybe it would be interesting to really try it also in a region with established wood burning problems. So a region that's reached out to us with issues for wood burning, or where a lot of citizens have complaints about this. Or maybe an urban area where we expect to have a little bit less wood burning. Maybe we see if we could still pick up some spikes or not. So really it will be interesting to see what's the possible scope of this technique. How broadly can we use this to really learn more about these, the distribution of these sources and flames. All right, that's everything for me. Thank you.
Yeah, thank you for your talk. I'm wondering if there's like any very urgent question. There will be time for discussion after the 3 talks. There's one urgent question by Margaret.
I guess I shouldn't qualify it as urgent. It's not necessarily urgent. You may have mentioned this at the beginning of your presentation. I'm afraid I missed the first few minutes, but you have a mechanism for people walking around to identify the source at a moment that it's peaking. So is there a way to say this, I smelt wood, I smelt incense? Are you capturing that from the person walking?
Yeah, so the idea is that basically the participants keep a diary. This is a low-tech implementation of it for now. Of course, if we really do this in a very broad scale, it'll be interesting to really do this, make this more user-friendly and less time-intensive for the citizen. But for now, yeah, the idea is when the citizen comes home and they noticed, so the device has a immediate LED feedback, basically tells you the concentration right on the device, or at least the range that you're in. So once they see that the color on the LED changes, we ask the citizen to make note of what they smell, what they notice, and then when they come home, to basically
Cool, that it's manually inputted, but that's cool. Thanks.
Yeah, all right, no worries.
Yeah, so we invite you to keep your comment or question about the presentation for the last part, and I will invite the next speaker, which is Gert-Jan Koch. Gert-Jan is a principal scientist at the Dutch National Metrology Institute. He has more than 15 years of experience in mathematical modeling and statistical analysis of measurement results. In the currently running European research project FUNsnm, he has been working on uncertainty evaluation method for air quality sensor networks.
Yes, thank you for this introduction. Yes, so I will speak about metrology and in relation to citizen science. So I will I'll speak a bit more about what I mean with this and metrology and metrological traceability. About calculating uncertainties, and then about challenges, how when we apply this scientific rigorous approach to citizen science. I will speak shortly just about some results in the FUNsnm project and some concluding remarks. Here you see with the red circle our institute, which is located in the south of Delft in the Netherlands. Yeah, so metrology, it's the science of measurement and try to make everything very rigorous. So, also in the last presentation, you saw 1 microgram per cubic meter or 10. And then you can ask, what does it exactly mean, this 1 microgram per cubic meter? And that's then, the scientific background of metrology. It refers back to the SI system of units. So we have the gram, which is a submultiple of the kilogram, and if the meter, so it's cubed meter, and they come back, they are derived from the SI system of units, and actually these units are defined in terms of fixed numerical values for certain natural constants. So for the second, there is a cesium atom, and there's some frequency, some physical phenomenon in this atom. We fix a numerical value for it, and from that you can at the end derive what is a second. Similarly, if you have the second and you fix the speed of light, so it's about 300,000 kilometers per second, you can derive what is a meter. Another constant is the Planck constant, h, and with that and knowing what's a second and a meter, you can derive what is a kilogram. Of course, this is not very simple, but you have to perform some complex experiments in a very advanced laboratory, and it's typically done at national metrology institutes. And in the Netherlands, VSL is that institute. So from the definitions and some physical principles, we derive what is a second meter in kilogram. And then you get primary measurement standards, kind of atomic clocks for distance with laser-based measurements, or you can also have a ruler. Then for mass, actually we have quite tangible mass pieces. And when we do this, an essential part of it is always to evaluate the measurement uncertainty. So we evaluate all kinds of influence sources and potential error sources, and then we come up with a result and say, well, this is accurate to about 1% or or 0.1%, etc. But then now we just have, well, primary measurement standards. Then we come to methodological traceability. So a measurement is methodologically traceable if there is an unbroken chain of comparisons or calibrations, including an uncertainty evaluation that relates a specific measurement result back to the definition of the SI units. So we started here with the SI definitions, which are at the top, and they are agreed on an international level by the BAPM and representatives of all countries in Paris. Then we have some complex experiments, and we get primary measurement standards. It's typically done at NMIs like VSL. Then we also do some more practical measurement set instruments and standards that are working standards. Then we calibrate reference standards and instruments from clients, or we also supply reference materials, for example, gas mixtures, where it says you have so much ppb or ppm of NO2 in nitrogen, for example, so certified reference materials. Then it gets to manufacturers, industry, and they use it again with their instruments, and then they can calibrate a sensor if they do, because cheap sensors are typically not calibrated. They are just, well, there's some claimed accuracy based on, production control and statistical assessment. Yeah, so this is what methodological traceability is all about, and also what we are typically also considering in metrology and in our institute. And of course, the lower you get in this pyramid, the higher the uncertainty becomes. And yeah, but also the more efficient or the more cheaper the measurements usually get. So for each application, you have to find a balance. As indicated, uncertainty evaluation is very essential in all these steps, because we finally want to know how accurate is a measurement. And for that, we have the guide to the expression of uncertainty in measurement. That's the also an ISO standard, but it's used by various standardization bodies, and it specifies how you can calculate a measurement uncertainty in quite general terms. Excuse me. Now, first step is to define the measurement Y often unambiguously, and that can seem trivial, but for example, but it's not actually always. For example, if you want to measure a distance of a rod, then, or of a steel rod, then it's not just about the length. You also have to specify which temperature, because it can expand at a higher temperature, and then, well, it's not there's an ambiguity in what you mean with the length of it. Then we have to determine all influence quantities that affect the measurement. For example, for the length, there's of course the reading of maybe my ruler, but there's also there can be also the temperature, or I do a temperature reading, and then maybe I want to correct it to another temperature, and then there's the expansion coefficient of the steel. It can also be, there's also the calibration uncertainty of my ruler, etc. So we have to determine all these influence quantities and their uncertainties. Well, we have to, of course, define how they relate to it. It can be just an additive model, like y is x1 plus x2 plus x3. And there might be also contributions that are nominally zero, but they have some uncertainty. Or it can be a more complex model. And then if you get then data, we have to we can calculate an estimate, small y of the measurement, and also its uncertainty with this uncertainty propagation formula. And here's Cy are the sensitivity coefficients. So it's basically the derivatives of this function f towards the different variables. Well, now we want to apply this methodological thinking to citizen measurements. And then, well, we define two challenges and related to what you just saw. The first challenge is, what is the measurement? Because we want to measure, for example, particular matter, but what does it mean? Is it the PM concentration at the inlet of the sensor system, which is the most, well, direct thing you could think of? But maybe we are also interested in health impact, and then you would think about, you would actually want to know the PM concentration at the inlet of my nose. And then, well, if you have the sensor somewhere in your clothes and there's some, well, inhomogeneity as there is in the PM concentration, then it can be different and has an uncertainty. You can also think of, should it be at, maybe there's some standard saying where to measure, maybe at 1 meter height in the center of the street, which is maybe different than what at the location of the sensor. Or also often in norms, there is there are limits on average PM concentration of one of the things above, and then average over a year, and then average over a complete neighborhood. But you can average over all available sensors, and what does it mean averaging over the neighborhood? Just the outside or inside as well. So if you want to apply this rigorous methodological thinking of metrology, citizen science, there are some challenges to make it, well, very rigorous and precise. And also, so the definition of the measurement very much affects the evaluation of the measurement uncertainty. Well, a second challenge, of course, is how to list and quantify all sources of uncertainty, because that and how to make the measurement methodological traceable. We need all these sources of uncertainty and quantify it if we want to really make well, the measurement traceable and with a reliable uncertainty evaluation. Well, we have sensor calibration, or at least some base accuracy that we believe, which is maybe given in the specifications of the sensor by the manufacturer. But of course, the sensor may drift over time. So at one point in time, at production time, maybe there was some accuracy, but it can change over time. There are interference and ambient conditions, so humidity, different temperatures, maybe also different gases. For example, when you're measuring NO2, there might be ozone as well. And all this can affect your sensor. And yeah, and it makes the uncertainty evaluation very challenging. And then maybe you have calibrated or compared your sensor with some reference at some point in your network, and then, well, establish an uncertainty. But then you apply it in another position, other location, where there are maybe unseen conditions with well, other temperatures, other interference, etc. And yeah, and the main problem, a big problem with this outside measurements compared to the lab environment where I'm from is it's a very much uncontrolled environment, of course. When you average sensors, it's not just averaging uncertainties or by like the square root of n, if that's the number of data points, but there can also be correlations between these uncertainties. So you have to properly take that into account. And it's similar when you're interpolating between two sensors. And also in the FUNsnm project, we did a little bit of work on that, which I will present later. Then, well, compared to the typical traceable measurements that we perform in the laboratory, there's the aspect of, well, operator uncertainty and trained personnel, quality system aspects. Typically in metrology, or at least in labs, we have quality systems which specify that the operator should be trained, and well, it was also mentioned already in the last talk. In citizen science, that there's not such a thing typically, and well, so we have to incorporate an uncertainty for that in our uncertainty budget and uncertainty calculation, but it's a challenge how to do that. Then I will say a few words about the European research project that we're currently running. It's fundamentals of sensor networks in sensor network metrology. So it's a group of metrology institutes and universities, and also some other parties like air sensor network operators, and not just for air quality, but also joining together. And we aim to develop methods for assessing the trustworthiness of distributed sensor networks. So we're looking at mathematical methods for uncertainty propagation, for in situ calibration. There's work on data quality metrics. There's some development of a general software framework. And actually, there are three main applications: the energy distribution sector, also sensors in manufacturing environments, and in environmental monitoring. So air quality measurements are just one small part, 1/3 or so of the FUNsnm project. What is a project in the metrology partnership, which is part also of Horizon Europe. So what did we do for now? So the project is now finished, almost finished its first year. We looked at the effect of correlations between NO2 sensor data when averaging. So we took a data set of the COMP data sets, which is a nice data set of collocated measurements, and you can freely available. See the link here below. Well, we took 3 sensors of same type and about 6,000 readings. Well, and then you can compute, of course, a mean value. But then we had to calculate what is the correlation in the uncertainty of this sensor. So first there's a very low uncertainty reference sensor collocated. So first we determined or estimated a single sensor uncertainty, which is like a bit more than 4 ppb, just based on this comparison. And then we calculated the errors of the sensor, and then we fitted, and then on the error signal between reference and sensor, we looked at the correlation behavior of that signal of basically the sensor errors. Still, we see a very periodic behavior, so which is not just linked with the value of the NO2. So also in the errors, there's quite a high temporal correlation. So we split on the temporal correlation, as you see here. So we split the correlation in a temporal part, which is shown here. And for the spatial part, we didn't really have data. We just saw that the 3 sensors had very similar errors when collocated, so they were not really independent. And then we just put a number of a typical number of 1 kilometer for how we expect the correlation to diminish if they are at more distant locations. But that was a bit just the estimate we made. What we then see if you average all this, the uncertainty of this average, if you would just take 4 divided by the square root of 5,784, you get this very low uncertainty for this average, which is not so realistic. If we, because very low and it would go to 0, the more and more measurements you take. If we include this correlation model, we get a much higher uncertainty. Still quite low, but it can be more realistic. Another thing we did is looking at the effect of correlations in sensor network when interpolating data. That's a completely numerical study, actually. So we modeled how the distribution of the NO2 concentration could be. And then we modeled that with a Gaussian process network, and then the sensors had a certain uncertainty or a certain error structure, so certain covariances, and then we investigated how important it is to know this covariance structure. And so we estimated the NO2 fraction at this point here by fitting a Gaussian process model, and then by either knowing the correct covariance structure or just knowing the sensor, this uncertainty of single sensors without assuming any covariance, or just knowing or nothing about the sensor errors. Then you see the uncertainty of this point would be about 4 ppb there, and it's indeed 95% of the time right, what we would like to. If there are independent errors, then we get a higher uncertainty, but it's actually too high, well, as compared to with what you would like to have if you want to have a 95% confidence interval. And if you provide no information, well, things get a bit, well, mixed up or equal out, and then you get a low uncertainty, but it's actually too low. We recently presented these results at a metrology conference, actually in Hamburg. So conclusions. Well, we had the first part where we saw that it's challenging to apply the full scientific rigor of metrology to citizen science. There's challenges in specifying what exactly, well, what do you want to measure, define it precisely, and what are all uncertainty sources, and there can be really a lot of them. Then there can also be correlations in sensor data, and when you want to have a quite, well, accurate uncertainty evaluation, then that matters indeed. Of course, there can be other big uncertainty sources, but well, if you wanted to be precise, then it matters. And I think finally, I would like to state that I think very interesting to have this joint workshop with different projects joining together, with some with more practical, be more from the scientific and methodological side. And I will see also the talk by SOCIO-BEE later on. So thank you. That was my talk.
Yeah, thank you very much, Gert-Jan. I was wondering if there is maybe one urgent question now, or if we maybe move on directly to the last talk. Yeah, maybe we move on directly to Sergi's talk. So I have a few sentences about Sergi. Sergi Udina wrote a PhD in advanced engineering with his thesis, Smart Chemical Sensors, Concept and Applications. He is an expert in electronics for sensor interfaces and applied machine learning, and has more than 20 years experience in the research, development, and innovation field. Sergi Udina is currently working at Better Cities, which is part of the European Horizon Air Monitoring Citizen Science Project, SOCIO-BEE.
Thank you, Arefa, for the introduction. Can you hear me well?
Yes,
okay.
We can hear you.
Okay, I think that Bram and Gert-Jan had set up a very nice frame to go into this presentation. SOCIO-BEE is now in its final months. We've been swimming in the project quite deep for the last years, and I will try to get my head above the water, which sometimes is a little difficult to get outside of the framework of the project and present the results in a comprehensive way. But I will try my best. In this very early, I am presenting very recent results, and hopefully this is of interest for our audience. The title of the talk is addressing the challenges of citizen science air quality measurements in the SOCIO-BEE project, of which there were quite a few. Let's see, is this working like this? Okay. The parts of my talk would be an introduction first about the project. Then I named this regulation for air quality sensor system. It's more like tools for regulation rather than regulation, but you will see what I mean with this. Challenges in practice, of which there was quite a lot of practice in this project. The proposed solutions, what we have attempted, the outcomes of these attempts, and some conclusions. So what about the SOCIO-BEE project? The SOCIO-BEE project has different aspects. Perhaps the main one is the approach to citizen engagement that we proposed. It's called SOCIO-BEE because it tried a hierarchical approach to create organic communities which are stratified, are hierarchical, with different roles of different citizens. And for this, we use the metaphor of the analogy of the bees. The full community would be a hive, and then there would be a queen bee who is organizing the measurement campaigns and helping out and motivating or organizing a number of worker bees that would actually be doing the measurements themselves. And then we have the figure of the drone bees, which are people associated to a measurement campaign, not directly doing measurements, but perhaps doing dissemination, talking about it, or explaining what is being done. And the bears, which are interested in the honey. What is the honey? The honey is the data, the information we get from a campaign. So that was this pretty nice metaphor that got the idea of the engagement approach. Apart from this rather theatrical engagement approach, we had a number of technologies which were quite ambitious as well. First of all, we had a wearable sensor node, which in this case, it measured also PM2.5, the same as Bram presented, which has a number of characteristics. But from the point of view of metrology, it's easier than pollutant gases, because we are attempting also to measure NO2 and ozone, which are extremely challenging, especially in city science settings. Then we had a mobile phone that was a companion for this wearable that helped for visualization and relaying the data. This wearable did not have a GPS, this depended on the mobile phone. And then we had a desktop environment where the queen bees, the worker bees, would check how the measurements were progressing, then get the results of the calibrated data, because the data is calibrated in a cloud infrastructure, and then head back into the platform and follow up the process of the campaign. The pilots took place in 3 European cities, in Zaragoza, in Ancona, in Italy, and in Marousi, close to Athens, a suburb of Athens. And in these 3 places, intensive activities of measurement campaigns were carried out using this infrastructure that I have just mentioned, but with different targets, different approaches. So in Zaragoza, there was a strong participation of youngsters and schools. In Ancona, there was an involvement of elderly people, and in Marousi, the targeted people were commuters that probably were working nearby and living in Marousi, or people more in the middle-aged work class. Okay. So now I will talk about what is the status of regulation for air quality sensors. The framework is placed by the European Air Quality Directive, which has a first version from 2008, and this one built on the World Health Organization guidelines, which became a little bit outdated because I will present later they are evolving. But okay, so we have with these WHO guidelines that tell us, taking into account the whole literature of health effects of gas pollutants and health effects, what should be the limits for civil population. And then according to this directive sets limit or target values for NO2, carbon monoxide, NO, ozone, SO2, benzene, PM2.5, PM10, and lead. It also proposes a sensor system classification in order to determine if one sensor system can be used for regulatory purposes or can only be used for modeling, for estimation purposes. So there's different purposes. There's the fixed measurement, which are the official reference stations, indicative measurements that are almost as good as fixed measurement or comparably good, which can be used for regulatory purposes, and then objective estimations that have also can have a degree of regulatory value, but are less precise than indicative measurements, and modeling data which cannot be used for regulation. If we take a look at the World Health Organization guidelines, just to have an idea of what we're talking about, we see that there's been evolution from the 2005 guidelines to the 2021 guidelines. There's a tendency to reduce the limits that are regarded as accepted as exposure for the population, and they are pretty stark lowering of the limits. I don't want to go a lot into it. I wanted to present these numbers only to have an idea of what are the typical numbers we're looking at, below 100 micrograms, so on. Then, to develop and to implement these concepts or this frame set by the European directive, the 2008-50 directive, the European Air Quality Directive, standards have been developed and are in development, or rather than standards, in this case is a technical specification, which is another rank of official document, which is telling you how things should be done following the current framework, the current directive. Okay, and this standard for sensor systems is the CEN-TS 17660, which has two clauses. It has part 1 and part 2. Part 1 deals with gas pollutants, and part 2 deals with particulate matter. We've talked a little bit of both. Bram has done a very nice introduction for particulate matter. I regret that I do not have such a nice introduction for gases, but for pollutant gases. But it's also they are also known to have strong health effects, and I invite anyone to research about the health effects of NO2 and ozone, or to read the World Health Organization reports about it, which are always very useful and very interesting. Okay, apart from this technical specification 17660 relates in particular to classifying the sensor system, how one must, what actions needs a manufacturer to undergo to assign a classification to a sensor system. A manufacturer or an initiative, a technological initiative, it can be a community. So what should you do to certify the accuracy of your sensor? And it only relates to these actions. It leaves out the system preparation and the calibration, which is an action that before you go into certification, and it does not also concern what happens after deployment. It's an intermediate step after calibration and before deployment that happens to certify a number of actions and a set of actions that you have to do to certify the class of your system. Class 1 would be an indicative system. Class 2 would be an objective estimation, according to the slide I presented before. And class 3 is regarded as citizen science instruments, which are not fit for regulatory purposes. Okay, and it establishes this technical specification establishes limits of on the accuracy, on the expanded uncertainties, and this is very good that Gergen put forward some of these concepts in the talk before. So we're talking about uncertainty. There is limits set into the uncertainty that your system can have to be assigned one class or another class. Okay, and these uncertainties depend directly from the limit values set by the directive. Limit value is the recommended limit values of exposure of citizens. Okay, what are the challenges in practice to try to follow this approach? So first of all, if one attempts to follow the technical specification to certify the devices, maybe I should have introduced the need of certification. Why do we need to certify? Because if in the project you want to have outcomes that can have an impact, that you can go. So the idea of all this is, in the end, try to influence policymaking, try to inform policymaking. But if you want to inform, you need to also inform of the accuracies of what you're reporting. You need to know if what you're measuring is reliable or not. Okay. And this is in citizen science approaches, it is typically hard to do, and it's an open problem. So one way to go about it would have been to certify. But what do you have to do to certify? Sadly, in this technical specification, in the framework of an European project like SOCIO-BEE, which has a duration of 3 years, and there is 2 iterations of the technology, we would have needed 4 months between the technology is ready and we start the pilot to be able to go through the certification process. That is in case we had a certification entity, which is still not available, but that's another matter. Even if we tried to sell, we attempted to self-certify, we would need 4 months to follow the full procedure, which was not possible in the framework of this project. And unfortunately, it's not uncommon that projects do not have 4 months to go through a certification process. This is a common, typically, the projects are tight in timelines, and it was very much the case in SOCIO-BEE. We were very tight, to go into the 2 iterations of the technology and the engagement toolkits in 3 years. It was very tight. So it remains a challenge how we determine or estimate or give some idea of the accuracy of our measurements and our general reliability if we cannot go through this certification that the technical specification tells us to do. There were challenges specific to the 2 operation modes of the sensors. We call them wearable sensors, reportable sensors, but they could also work in a stationary mode. You can also leave them stationary and let them measure on their own. Okay, so there were 2 modes, one with a person, with a citizen scientist carrying the device on himself or herself, and the stationary mode where perhaps also a citizen scientist could leave the device in a balcony or somewhere outdoors, it had to be, and let it measure with a degree of protection, of course, but yeah, I will go into this a little later. So the challenges specific to wearable mode, one very strong challenge was similar to what Bram mentioned, but much worse. When you have a transition from indoor to outdoor environment, it's not only that the measurement data changes and can bring false measurements, it's that the sensors become unstable for a few hours, for some hours, so or maybe one day even. So the transients of humidity for the PM sensor behaves the same as Bram sensor. So the PM 2.5 sensor that we have on board is okay. It can deal with it. You can deal with it in the same way that Bram presented. But the toxic gas sensors are much more sensitive to this sort of transients, and really their measurements become invalid for a long time after they have been indoor and go out. Okay. This makes the user handling, the citizen scientist handling of the sensor much more critical. Where he goes, how he stores the sensor. So all this it makes it very critical. On top of this, we do very fast measurements. We did 10 seconds measurements. And whenever the directive or the technical specification requests us to do 1 hour averages, when you are using the wearable mode, this is not possible. This is not possible at all, because no citizen scientist is staying 1 hour at one place. The approach, the whole engagement approach, and the whole campaign activities approach that we defined in the project, we decided that it was not possible to have the citizen scientist stay at one place for 1 hour. We preferred to measure more places with finer grained temperature time windows. Okay. But this sets you completely outside of the possibilities of using the technical specification. Okay? That's a consideration we have to have. Then there is also battery management related issues. The system is powered by a battery, and if it's charging, if it's discharging, it can introduce additional risks because of the sensitivity of the gas sensors, especially to temperature of the device, which changes depending on this. So there's an additional challenge. And then there were challenges specific to static mode, which was selecting a suitable location for the node to stay there and nobody to steal it, or so that anything bad happened to the device, ensuring continuous power and connectivity, And also the static measurements require a higher bandwidth data pipeline because it's continuous, it's shooting measurements every 10 seconds. So it requires, when you have many of them, hundreds of them, then you need to, your data pipeline to the cloud and the calibration services needs to be streamlined. And there's challenges there also. So what were our proposed solutions for these challenges? So we have adopted, after first iteration and knowing, having a good picture of the challenges, how challenging these challenges were after the first iteration, which happened in 2023, okay, spring 2023. We decided to go for a multi-level referencing and traceability for uncertainty propagation. So the same that Gerd-Jan presented, we need to have clear steps and the uncertainties on the different steps to go up to try to go up to the references and to our values we can rely on. So first we needed to rely on low device-to-device dispersion, so good reproducibility between devices, and this is something we are very, very, how to say, we put a lot of effort in this in Better Cities. So this is one of our strong points. We really do monitor and control very much the device-to-device reproducibility. Then you needed access to a reference station, which is sometimes can be hard, especially for science, for citizen science communities. And the availability of secure outdoor exposition point to place secondary references. What I mean by secondary references is a number of devices, of wearable devices, equivalent devices, many of them with a redundant measurement in one point. So in one point, we have measurements on different devices in the same. Okay. Level 1, level 2, level 3, 4. So continuing and elaborating on this multi-level referencing, let me see, I am covering. I can read. Because your images I'm covering my slide now. Okay, so in the level 1 would mean collocation with an official reference station. So we have both measurements, the measurement of the devices, of the SOCIO-BEE devices, and the measurements of the reference station in the same place. The level 2 would be redundant static devices placed in the same place, exposed to the same atmosphere, to the same air, and then to estimate the device-to-device dispersion in that situation. And the level 3 is while in wearable use, schedule measurements. So when the citizen science is itinerating, is moving around, some of these measurements should happen at the level 2 reference point, coincident at the level 2 reference point. So in this way, we can mix and match, and we can see the discrepancy between the wearable measurements and the reference static measurements. Okay. There is an initial device-to-device dispersion estimated at factory calibration, and that sets a lower boundary. We know that at least the device-to-device dispersion is this one, what we set at factory. And then from that, we expect an increase in field conditions. Okay, let me see. Yeah, here we are. So here I present the approach of how to propagate the uncertainty that we used and we proposed in the framework of this work, which is taking the squared sum of 3 magnitudes. We have a cursor, yes, which is the main uncertainty of the reference, the main reference that you use, which has also to be traceable and so on, but you have a certified uncertainty. Then the uncertainty between the collocated devices, estimated the collocated devices, and the reference, which is independent, these two. And then these 3 are dependent, so this is why I take the maximum, which is the device-to-device dispersion estimated at the different levels. Level 1, we could place here also at calibration, but it will also be lower, so it wouldn't make sense. Device-to-device dispersion, or either in collocation, either at level 2, the device-to-device estimated dispersion at the reference points, or at level 3, which is estimated in this process of getting a citizen scientist with his or her device close to the reference point and see what is the discrepancy. That would be a level 3 dispersion. the maximum of this. I place it here in red because level 3 because, well, first of all, it's going to be the greater one. But in this analysis, I have not used it. We are still analyzing the data, and we don't have figures for this. I only have figures for the uncertainty estimated at stationary mode, not wearable mode. Okay. So let's see, wearable users. Okay, there's another factor that is used for to deal with the challenge of the user handling of the device, which is, as I mentioned, was a very strong factor in the uncertainty, and is the embedded validation. So the device does a number of algorithms and computations inside, statistic computations of the data it's gathering, raw data, because remember the calibration is performed on the cloud, the full calibration. But in the device itself, it analyzes the raw data and it decides if the gas sensors are in a stable measurement mode or are unstable. They have seen a very large transient and are not yet stabilized. And for that, there is an LED that has already expired here. Let me see. There is an LED that gives a number of blinks. So it's so the green blink is about the connectivity, if it's connected to the mobile phone or to the Wi-Fi, and then the double red blink means I am not yet providing stable measurements, and this is useful for the citizen scientist to check if do I need to wait more to take a measurement here, or can I take it already? And it's useful because if the citizen scientist is blind, it's very easy that you get bad measurements. What are the outcomes of these approaches? Well, let's take a look at the collocation activities that we did at the Evolution pilot, and we had these measurements at I think it's an urban background station with not very high levels of NO2. The results we got though were we are happy with them, which were around 20 micrograms per cubic meter of uncertainty at the level 1. Okay, discrepancy with the reference. I want to thank Amir Hossein Hassani from NILO who provided these graphs. We did a third-party analysis. We could have done it in Better, but we prefer to do it externally, and so he has provided the graphs. So thank you for that. And then we looked, so the error with the uncertainty with respect to the reference and the device-to-device dispersion, and in this case we got a level 1 dispersion of 6 devices of 15 micrograms per cubic meter, and a level 2 device dispersion, which means the 3 devices we had at the reference point, where the 3 equivalent devices were at the same point, we got a dispersion of 12 micrograms. So in this case, the one that dominates is the one we calculate at the collocation. Okay. Similarly, for ozone, we did the same. We got 36 microgram per cubic meter uncertainty, and we got a device-to-device dispersion of 25 micrograms per cubic meter, both in the collocation and in the reference point. And for PM 2.5, unfortunately, we had no reference data available. It was only measuring PM10, which is shown here in this. So here we show the black is the PM10 reference data, the blue is the PM 2.5. It makes a lot of sense, these two graphs, because PM10 has always to be above the PM 2.5, but we cannot draw, I mean, it's only a qualitative estimation. Okay, it looks good, but so what we did is we used the reference uncertainty of our factory calibration, our in-house calibration. We have a reference equipment in-house, and we use that, okay, as an initial estimation of the uncertainty. And we had it is important to note that we had much lower dispersion. So the measurements with the optical measurements of PM 2.5 are much less challenging in the sense to get decent accuracies, to get good accuracies than for gas pollutants. It's much harder. It's much harder. Okay. So these were okay. We got 6 micrograms per cubic meter for both magnitudes. If we put all of this together, we got estimated total uncertainties for NO2 of 25 micrograms per cubic meter, for ozone 44 micrograms per cubic meter, and for PM2.5 10 micrograms per cubic meter. And this would be equivalent for NO2, it would be equivalent only taking into account the expanded uncertainties, a class 1. It would be a class, so it could be indicative. For ozone, it would not be class 1, it would be class 2, and for PM2.5, it would be class 1. But we have to put this in parentheses because, as I said before, these classes are assigned for hourly averages. Okay, so it's another completely different time frame because we are trying to draw an equivalence for measurements that are taken every 10 seconds and to draw conclusions for measurements that should be averaged for 1 hour. So this is a very big leap. Okay, but anyway, just to set a mind frame. So what do these uncertainties mean? It means that we are probably there in the if we do 1 hour averages, we could probably be at class 1, we could probably be at class 2. Okay, and here I present a nice map provided by the University Polytechnica de Le Marche by Nicole Moresi. Thank you very much. This is a map of PM2.5 done with the citizen science measurements campaigns in Ancona. Remember that this is mostly elderly people, and we see we similarly to what Bram presented. So we have candidate sources here close to the port, okay, and in the main street of the city. The analysis of this data will take months. We are not, as I said, this is all very recent data. I am presenting very recent findings, and it will take time. But this is just a small glimpse of what might be coming in following publications and so on. Okay. So the conclusions. In citizen science campaigns, the possibility to calibrate or certify sensors is often non-existent. Time constraints, accessibility to reference stations, to the collocations, etc. Unknown or bad field performance of sensors used in citizen science can render time-intensive campaign efforts ineffective to elevate these results to policymakers to have any credibility in this data. So the most reliable way to examine sensor calibration techniques, the factory sensor calibration techniques or initial pre-deployment sensor calibration techniques, is the accurate estimation of uncertainties in field conditions after deployment. This, which may seem very trivial, but this is not what's typically done. Because to truly estimate the sensor performance and uncertainty, the temptation of using field data to recalibrate must be resisted. If you are using field data to recalibrate, yes, you lower your uncertainties a lot, of course, but then you don't know what is your uncertainty. You cannot know your uncertainty if you are using field data to calibrate. So this almost never happens. There is always a drive to try to report the lower uncertainty in training. But if you have a training uncertainty, yes, you can use cross validation, you can use some approaches, but it's not a real separated estimation of uncertainty if you're using that data to train the system. This is important. Maybe for some people this will be familiar, for some it will be completely strange. I understand, depending on the audience, but it's a concept to have into account whatsoever. In this work, a multi-level traceability approach has been introduced to estimate the sensor performance in wearable devices and citizen science settings. It has been presented to complement somehow the technical specification 17660 when fast deployments and iterations are required, and also when hourly averages are not available. Okay. I introduced this concept from factory to campaign. This is what we have done. I mean, the sensors were out of the factory and straight into the campaign. And what do we get? So this is what we get. Is it good enough? But it's arguable, okay? So the preliminary assessment of the SOCIO-BEE wearable sensor node performance show that a relatively good performance is achieved that could correspond to perhaps a class 2 equivalent in terms of total expanded uncertainty. Remember, this is for stationary usages. It's not only, it's the uncertainty of the references and the stationary nodes that people had in their balconies and so on, not for the one that was being carried around. The one that is being carried around, I can assure you, had very strong challenges in the analysis of the gas pollutant data. PM2.5 was similar to what Bram presented, but the gas pollutants were hardly usable in many of the wearable experiences, okay? Well, of the itinerating experiences. But for stationary usage, class 2, perhaps even better in some cases, after without any additional corrections after deployment. It is possible to do correction after deployment. Of course, you can do that. You can dedicate some time to that, improve that. It's possible. But in this case, my focus was to present the uncertainties of this approach. So the large data sets that we have acquired, which are pretty cumbersome, are still under analysis, of course. We still have to publish them. And we hope to release several publications soon and give dissemination about this. So expect things happening on this front, okay? And yeah. Goodbye, everyone. Thank you for your attention. And this is credit of the model of this nice model of the flying bee that this has been accompanying us in the talk. And special thanks to Amir Hossein Hassani and Nicole Moresi. And that's all. Any questions?
Yeah, thank you very much, Sergi, for your talk. I'm just looking at the time. I mean, like it's 12:30, so we arrived at the end of the official announced time. So of course, whoever has to go should go, but we'll take a few more minutes to discuss this representation. With the people who can stay. So I would like to ask the audience if there is maybe like some question to one of the speakers, or maybe like one question for the three speakers.
Yeah, I can ask a question. I think during the three talks, you talk a lot about the uncertainty of the sensors. And I can identify one topic that has been in the three of the talks that was about this certification or having a stamp on the sensor that ensures the credibility. So that's getting the instrument certified, but you also talk about training the citizens to get more accurate data. And I remember, for example, was this like, okay, the sensor that was carried by our colleague was much clearer data. And I want to pose this because we're talking about citizen science, a little bit of a challenge question to three of you. So if we are getting, instruments certified and get to go through a lot of calibrations, validations, that will certainly increase the price and will leave behind some of the do-it-yourself sensors that cannot go through that process. Only the ones that come from manufacturers can go through that process. But also, if we are required citizens to go through so much training, in order to be able to capture this data, be able to be digitally very active, etc., will this not introduce biases in who are collecting the data? We already know citizen science is a field for white men with some certain education. Not pointing any one of you, the three of you, but how will this be impact, and how do you see the future of balancing these two needs for increasing trust? Thank you. It's for the three of you.
Yeah, maybe I can start. So I think from our point of view, the sensor accuracy plays less of a role because we really only look at these events. So we decide a certain threshold and then we pick up everything above a certain threshold. That takes away a lot of the dependence on the exact number that's being measured. Of course, it's a very coarse-grained way of going about it. But you know, that's the price you pay. You will lose a lot of data points this way, which might have been useful. But the idea is that if you do the experiment on a big enough scale, then you'll pick up the hotspots anyway. And then we really care about accuracy later on if we would do the stationary measurement that really gives you continuous data. So these mobile measurements really are meant as indicative. So that's the sensor part. But then the participant part, yeah, that's a constant struggle to find a balance. Also, when it comes to time investment, you don't want to give people too much training. You really want to. So I think really it comes down to making the device as simple as possible, and also making the data processing as tractable as possible. If it means, I think, you know, in the end, the story has to be, if the citizen scientists' life can be made easier, we should try to do it as much as possible, because they are really delivering a service to us. So we should try to make everything as user-friendly as possible. And if that means we have to go through a bit more lengths to do data cleaning and data processing afterwards, that's the price you pay, I think. But rather that than having a complicated device that requires some 2-hour training workshop to actually operate. That's certainly not the idea. Yeah, but it's always a struggle to find a diverse group of people, motivated and enthusiastic to do these type of things. I mean, you always attract a certain profile with these kind of things. So, yeah.
Maybe I can. Gerjan, do you want to say something?
Yeah, well, just you can go first. Just some small comments, but yeah. Okay, well, yeah, I was just thinking. Well, that's well for participant for the second question on the number of participants. The more and more it gets, just I think maybe in future, if it's standard integrated in your phone or in your car or so, then anybody who buys a car or a phone and clicks just on the Google default settings or so will be participant. So in that way, maybe there will be a much more there will be more data and more diverse people using it and collecting data, and also in different areas. So I'm also wondering now if the area is in Hove, if there's a particular population where they were walking, well, I'm making it more accurate and so and all this type of things. I think at certain points, well, we should have a lot of automation and not having us anymore looking at the data. But if there's a lot of data, well, if there's really a lot of data, maybe different effects can average out a bit more, maybe. And then, yeah, well, we should strive to a lot of automation and of pattern recognition and training machine learning models, and so to make more sense of this data. But this will still require a lot of research. And at the short term, I think we will keep this problems that you indicate, that that the reliability is not yet what we would like to have it. But Sergi, you would like to comment as well, so.
Yes, so I think what I presented tries to address what Nuria has just asked in two aspects. You know? So how can you, and if you don't have the possibility of going through certification with a do-it-yourself device, what can you do? Well, what I have presented, what we have done in the SOCIO project, is precisely this idea of trying to do strength in numbers, try to have many devices concurrently at different places at the same time, to try to propagate uncertainty in a plausible way, in a way that makes sense. But for that, you need access to a reference, first of all. You need to be able to do a collocation with some devices. Then you need to have references, static sensors close to your campaign, references measuring at the same point, and then some devices itinerating. And this is precisely the idea. This is a proposal, of course, can be completely discussed, criticized in many aspects. But it's a proposal of how to go about when you don't have a certified device. You want to know the reliability of your measurements, and you can have many devices, and you want to have citizen scientists. So this is basically the proposal. And then in the part of education, what we have tried is to make the device as smart as possible. Probably from when you have the manufacturer's knowledge, you can implement a lot of that knowledge into embedded signal processing and embedded assessment of the quality of the measurement already from the raw measurements. And this is what we have done. So to let the citizen know if they are doing good or not good, or the sensor is stable or not stable, to try to implement as much intelligence as possible inside the device. And this is also possible for DIY approaches probably in open source concepts that people keep building on the reliability of the self-assessment of the sensor. This would also be a nice way of going about this sort of projects. No?
We will take a last question, which was written by someone in the chat. So I will read it out. It's for Sergi. How will you estimate the uncertainty of the very short measurement period of 10 seconds? Sorry, this was not very clear. On top of that, uncertainty of 20 microgram per meter cube for NO2 seems problematic in respect to the proposed air quality limit value of 20 microgram per meter cube. What is your view on this?
Yes, it's problematic. The accuracy that you can get, in general, it's very hard to get good accuracies with NO2. We know that the health effects make differences even for values as low as 10 micrograms per cubic meters. There are observed differences in the health effects. And going that this is an extremely challenging meteorological problem for the available instrumentation, it's very difficult to measure so low. We're talking about ppbs. Think that the typical wearable devices that historically have been used for industry were in the ppms, 1,000 times higher concentrations. Here we're talking about 1,000 times lower. It's very challenging. And yeah, it's problematic to measure so low. So of course, the World Health Organization can go lower and lower and lower, but the question is, can you measure that? Well, we don't know. I mean, the reference stations can, but we know that NO2 is hyperlocal. So it has very local effects within a city. So the data from a reference station is not really telling you the picture. But anyway, that's another discussion. How we went about the 10 seconds is when we had the stationary device collocated, we are doing 1 hour averages of the collocated device. So we're comparing 1 hour averages with 1 hour averages. From there, we derive an uncertainty. Okay, and we sort of assume that uncertainty, that discrepancy with the reference in 1 hour averages would be the same in 10 seconds. It's not possible because probably the reference is not, some reference do measure so fast, but you don't have access to the data. Typically, it's only the public data is 1 hour. So it's complicated. If you had access to a final grain reference data 1 minute, then it would be closer. But typically from our experience, it should not be very different. So if a device is for several weeks has an uncertainty with in hourly averages of around these 20 micrograms, then if you take the 10-second measurements, you assume that it's going to be an equivalent uncertainty of the measurement. And if the dynamic, but of course, what is true is that the response time of the sensor is not so fast. So this is why normally we ask citizens to stay at one place for at least 1 minute to at least account for the response time of the sensor. But yes, there is an assumption. There is an assumption, which from our experience, it's not a big leap of faith. It's an assumption that you can defend from our experience, but it can be criticized. That's the answer to TESS.
Yeah. We'll take a very, very last question because we are over time already. So Milena, please.
Hello. Thank you for the presentation. And my question is not only for the presenters, but also to the audience. What is more important, to have the right data, correct data, or to know the trend? Because, for example, if with the low-cost sensors, we measure the levels of NO2 around the schools and find that the peaks of concentration was in the morning when all the students come to schools, and after the education process when they go home. So if we want to take some measures, we could implement, for example, school street. And if we want to close for the traffic all around the surrounding streets, that means more efforts and cost to prove this with more accuracy equipment. But if the school and parents and students decide to implement a school street in peak hours, just to close the nearest street for the traffic only when the children come to school and go back, that it's not need for the political decision. So it depends on our needs to know about the trends and the situation, and to find a better decisions. So what do you think is really need to have accuracy data, or just to have a trend line and to investigate and to invest more money when we find a real problem? Thank you.
Just because of time, I will maybe allow only one answer to Milena.
Okay, well, I did want to answer something to this, but now, of course, I'll be the only one answering, so I feel a bit guilty to my co-host, but whatever. So, I mean, related to this, at VMM, we also have a project ongoing currently, which is called City Track, which does exactly this, these mobility changes in cities in urban context, and tries to see the measurable impact on air quality. I think, you know, from the point of view of policy making, certainly if you have a trend, and you could try and do some policy change to counteract that trend, right? So if you see peaks in the morning around the school, then you can implement the school street, and presumably the air quality will have improved. I think the typical problem, though, is that to really motivate these changes, you want to have measurable effects afterwards. And I think that's where the accuracy comes into play, is that you don't just want to have the most accurate data before, because of course to diagnose a problem, usually a trend is enough. But if you really want to determine, and that is something that you know, local governments and politicians often want to see, is what is really the measurable impact of these decisions that we made. That often becomes trickier, especially with gas pollutants. Sergius has talked about in his talk. It's very tricky to get down to the level of accuracy where you can really see the effects of these mobility changes. And it's still, I think, an ongoing debate, what really is a measurable change or not. So that's exactly what we're trying to determine, or one of the questions that we're trying to determine in this City Track project. Yeah, I think that would be my answer, but I don't know if that is a satisfactory answer.
Yeah, I wrote my email address in the chat. Yeah, please, if you have like question or comment to the speaker or comment about the event of today, you are very pleased to write us. And yeah, I would like to close the webinar of today. I think that the goal of this webinar was to bring together three EU projects that has been running partially in parallel. Yeah, citizen science project involve many different partners, and always have to find a balance about the scientific relevance and precision of the question and the sensor, and also as well to be accessible to the citizens that we want to involve and reach out with the project. So yeah, I think that we managed to open a platform for opening the dialogue between those three projects, to start a dialogue about exchanges of expertise, and maybe also suggesting solutions that can be relevant for other projects. I would like to make a final announcement. For this, I will share my screen for last time. SOCIO-BEE, as Sergi told, is coming to an end at the end of this month of September 2024, after 3 years. And yeah, and on September 18th, so in about 2 weeks, a bit less than 2 weeks, we will have a final event closing this 3 years journey with the bees, the hives, and the honey data. There will be talks by different partners of this consortium, as well as reflection and discussion about what we have learned, what we have developed, and which challenges we have met, and we try to overcome together. So you are very welcome to join us, to register. I think that the registration link will be put on the chat. And thanks again the three speakers for the expertise and time. I thank you for joining us. I would also thanks Paul, who was in the background taking care of the Zoom technicality. And I wish you a pleasant rest of the day.